We are continuing our discussion about chemical equilibrium by taking a look at K. In a previous video, we talked about setting up the equilibrium expression, taking concentrations of products divided by reactants, each raised to their coefficients. We've talked about what that K value means in terms of being small, intermediate, or large. And so here we're going to now take a look at calculating K. When it comes to determining K, there are two primary ways to do this. We can do this from given equilibrium concentrations. This one's straightforward. We just write our K expression, we plug the concentrations in, we get our calculation. The other possibility is using initial concentrations, and in this method we would use something called an ICE table to find equilibrium concentrations. So first we'll take a look at finding K from equilibrium concentrations or pressures. So looking at problem 1, we've got this reaction of carbon monoxide with hydrogen to produce methanol, CH3OH. So we're first asked to write the Kc expression for this reaction. So Kc is going to be the concentration of my product raised to its coefficient divided by each reactant raised to their coefficient. So my hydrogen has a coefficient of 2. I need to make sure that my hydrogen concentration is squared. Now on part B, we're told the equilibrium concentrations are such that the carbon monoxide is 2.58 molar, hydrogen is 0.28 molar, and methanol is 2.93 molar at 210 degrees Celsius. So we've got equilibrium concentrations. We can plug this into our K expression and calculate K. So it's going to be my methanol concentration, 2.93, divided by my carbon monoxide, 2.58, divided by my hydrogen, 0.280. And we got to make sure we square that concentration. So this is going to give me a K of 14.5. So remember what our Ks are used for. We said the purpose of K is to judge the extent of our reaction or to describe the position of our equilibrium. So we're asked here the position of the equilibrium. So when we're asked that, we're looking, is K small, intermediate, or large? In this particular K here, it is greater than 10 to the negative third, but it's less than 10 to the third, which means I have an intermediate K. Now we said that intermediate K was going to mean that I have comparable, significant, measurable amounts of both reactants and products present at equilibrium. So my reactants and products are present in significant amounts. And if we look at our concentrations, hopefully this makes sense. So at equilibrium, I've got 2.93 molar of my CH3OH formed, but I still have 2.58 molar of my reactant left over. So I have significant amounts of both reactant and product present at equilibrium. That will be true of our intermediate Ks. So this example we just looked at, we had set up our K value in terms of concentration. But as we talked about in a previous video, K can be in terms of concentration or pressure. Now, they're not going to be the exact same K value because concentration and pressure are not equal, but they are related. They're connected to one another. And so Kc and Kp are going to be connected to one another through the following equation. So we have the equation that Kp equals Kc times RT to the delta N, where delta N is our change in our number of gas moles. So our product moles minus my reactant moles. And so if we go back to problem 1, we had this reaction of gaseous carbon monoxide with hydrogen gas to produce our CH3OH. And we calculated Kc for that reaction. We found Kc was 14.5 at 210 degrees Celsius. So if we were to plug into this equation to determine our Kp, we would need to know our delta N. So delta N is going to be my product mole. So that's the coefficient right here for my CH3OH. That's 1. My reactant moles is going to be 3. It's going to be the 1 from the carbon monoxide plus the 2 from the hydrogen to give me the total of 3 for my coefficients. So my change is going to be that 1 minus 3. So plugging into our equation, we plug in the Kc of 14.5. R is a constant. It's our ideal gas constant in terms of pressure. So that's 0.0821 liters times atmospheres over moles times Kelvin. Times our temperature. The temperature is the temperature in Kelvin. So we're converting that 210 to Kelvin by adding 273. And we're taking this entire quantity, so it's R times T raised to the delta N. And that is going to give me a value of 9.2 times 10 to the negative third. So if I know my constant in terms of concentration, I can convert it to pressure and vice versa. So we said there's 2 ways that we can calculate K. K can be determined if we know equilibrium concentrations, or we said that another method was going to be using something called an ice table. And this is done if we have only partial information. So we have initial concentrations, because we know how much material we start with when we do our reaction. And maybe we have 1 equilibrium concentration. So this would be a scenario like you guys would see in lab, where you start off, you measure certain amounts of materials, but maybe only one of your materials you can actually measure easily at equilibrium through something like a titration, which you would do in lab. So you have 1 equilibrium concentration, and you're going to use the ice tables to determine all of the other concentrations. So here, we're told initially we've got 1 molar of the nitrogen monoxide, 1 molar of chlorine. They're added to a 1 liter container. As a result of the reaction, the equilibrium concentration of NaOCl became 0.96. So we're told to use the ice table methodology to determine the value of the equilibrium constant. So the way this works is I need equilibrium concentrations for all of my substances, and I only have 1. We're going to use the ice table to figure out the other equilibrium concentrations. Then we can plug it into K and calculate our constant. So to set up the ice table, we take our balanced equation here, and underneath it, we create 3 rows labeled I, C, and E, where I stands for initial concentrations or pressures, C is our change, and E would be our equilibrium concentrations or pressures. And we start off by going ahead and plugging in the information that we're given into the table. So I'm told initially the NO is 1 molar, the chlorine is 1 molar. My product we can assume is 0. We will always assume that we have no product before the reaction starts unless we're told otherwise. Because if my reaction hasn't started yet, we don't have any product. The other thing we were told is the equilibrium amount of the NaOCl. So I can plug in 0.96 molar. So now what we're going to look at is I know the initial concentration of my NaOCl, and I know its equilibrium concentration. So it's a product. It starts at 0. It's going to increase by some X amount, and that will be equal to 0.96. Now, I've put a 2x here. My change, so we know as my reaction proceeds, my reactants are going to go down by some amount. So that's my change. The reactants go down by some amount. And that amount is based on stoichiometry, on their mole ratios. So my NO has a coefficient of 2, it's going to be going down by 2x. My chlorine has a coefficient of 1, so it's going to go down by 1x. And then my NaOCl2, it has a coefficient of 2. It's a product. It is increasing by 2x. So ultimately, we're looking for that equilibrium amount. So the way we get that equilibrium amount is we go down each column and we do exactly what it says. So my NO is going to be 1 minus 2x. My Cl2 is going to be 1 minus x. And then we know that my NaCl is going to be 0 plus 2x. We are now using this information to figure out what x should be. So I'm going to take that equation and I'm going to rearrange to solve for my x. And I'm going to find that my x is 0.48. We're going to plug this back into my ice table where I have x. So 1 minus 2x, that's going to give me 0.04 molar. 1 minus x is going to give me 0.52 molar. So plugging into my K expression, K is going to be the concentration of my product raised to its coefficient divided by each reactant raised to their coefficients. So I have the NaCl, which is 0.96 squared over 0.04 squared times 0.52. And that's going to give me a K of 1.1 times 10 to the third. You guys are doing something very similar in lab when you have your kinetics or your equilibrium concentration experiment. You have an experiment in which you know your initial concentrations. You did titration to figure out the equilibrium concentration of one reactant. You're setting them up into ice tables to figure out your other concentrations so you can determine your K value. Now, if we were to ask to calculate Kp, we're going to use our Kp equals Kc times RT to the delta N. So I'm going to plug in my Kc of 1.1 times 10 to the third times R, 0.0821, times my temperature. We were told a temperature on our worksheet of 25 degrees Celsius, which is 298 Kelvin. And then my delta N is going to be -1. So we're getting that delta N by my moles of product being 2. My moles of reactant will be 2 plus 1, which is 3. So product minus reactant gives me -1, which will give me a Kp of 45. So again, we can find K two ways. If we have all of our equilibrium concentrations, we can plug it into the equilibrium expression, we can calculate K. If instead I have one equilibrium concentration, but I know my initial concentrations, we can use an ice table to find equilibrium concentrations. Now we're going to get very, very familiar with these ice tables. We're going to use them in later videos and worksheets because more commonly K is going to be known. And if K is known, it tells us what our equilibrium mixture looks like. It's a constant, and so we can use it to get equilibrium calculations.